You've already submitted homework 4C, and on homework 5A, that's going to be due on Tuesday the 5th of November. Now, ordinarily, I would have had that due a week from today, but since we're not meeting next week, I didn't think there was any harm in pushing the deadline back until Tuesday of the 5th of November. The one caution I'll give you, though, is that homework 5B is due on the following class period, on Thursday, the 7th of November, and that class set is in the handouts that I've just given you. If you look at the notes for the 29th and the 30th, it tells you what homework 5B consists of. There isn't any change to our schedule for Lab 9. We weren't going to meet together in Lab next week anyway, since you're doing the independent lab design assignment. So you should still upload your handout to MU Online by next Tuesday at noon. And then you have, even starting now, if you'd like to run that experiment, you have access to the lab and can run the experiment anytime between now and next Friday. And at the end of next Friday afternoon, the equipment won't be available any longer, and then the lab report is due on the 5th of November.
We don't need to wait on you to grade the handouts.
Excuse me?
We don't need to wait on.
No, you can begin conducting the experiment. You don't have to wait for comments or anything from me. I'll try and grade those as quickly as I can, and I'll provide comments in MU Online as I do that. There's a location where instructors can type their feedback as they're grading within MU Online, and so I may have some suggestions for you. Do you get alerts when I have graded something? I never know when I'm typing in comments if it just goes into the void and you don't ever know that they're there. Have you submitted? Yeah, well, when you look at your grade for the lab handout, I think if you click on that grade, it'll probably pull up any comments that I've got for you. Was there another question over here? No? Okay.
Oh, where at MU Online will post that at? I know we'll go.
The lab handout?
Yeah.
It's just right on the front page.
You'll make it.
Yeah, if you click on the link for the course, it's the very first thing that you see is the course content. And that's an assignment in the course content. So if you click on the link, then it'll bring up a page that allows you to browse to a location on your computer and upload the file. Levi?
You actually want in the lab report,
a whole lab report, yeah, full-fledged. Yeah. This is the lab report that counts more than any other. This is the one that goes in the course portfolio that ABET comes to see, and they evaluate with all their wisdom whether or not we're meeting the objective of helping you to learn how to design and conduct an experiment. All right. So next week, it's all independent. The week after that, a bunch of stuff comes due. A homework assignment on Tuesday, lab report on Tuesday, the 5th, and then another homework assignment on the 7th. The good news is with Chapter 5, basically every problem can be solved with one equation. And you're going to learn that one equation today. All right, just a couple of comments about the lab reports. As I was grading the lab report that you just recently submitted, there were a lot of common issues that I didn't want to write the same thing over and over again, so I just thought we'd take a moment to talk about it here in class. The first thing is that when you're preparing a graph with data that you've taken in the lab, let's say you've got 5 data points, it can be a little bit misleading if when you put your numbers into Excel, let's see, what did we have? Reynolds number and K value. Many of the curves that I saw looked like that. And you don't know, based at looking at the curve, how many data points have been used to define that curve. You know, if it was 1,000 data points and they actually were along that curve, then maybe the curve would be meaningful. But sometimes what Excel will do is it will imply a curved relationship when really it's just scattered data. You know, if the actual data looks like this, then who's to say that it actually should be connected with, you know, a nice smooth curvature like that? And so to avoid any false representations of what the data is really saying, when you've got very few data points, what I'd suggest you do is you first of all show the data points. Have those tick marks there that show where the actual data is, and then connect them with a straight line at most, because that's the most we can say is that the data is connected, and there may not even be a trend in the case of that K value versus Reynolds number. You know, with only 5 measurements, it may be difficult to say that there was a trend, other than, you know, maybe you could put in a regression. You know, if it's gradually increasing like this, then maybe the trend is that. And if you think about it, that's a little bit closer to what was depicted on the handout itself for Venturi meters. The handout itself said that Venturi meters are going like this, where it's Reynolds number versus K value, depending on the D to D ratio. And so that's just one comment, is don't select the graph type that gives you smooth curved lines, and especially don't forget to include the actual data points themselves, because those are important. Any follow-up questions related to that first point? Yeah.
Can you upload instructions on how to actually put graphs up on the new 2013? I was very confused.
Sure. I'll prepare a screen capture recording, and I'll do some graphing tips. I'd be happy to do that.
You can connect it with straight lines with
Yeah.
columns.
Well, that's a graph type that you can select. You have the option of choosing that, and I'll be sure to differentiate between the two in the video that I make.
You know what
No.
it's all off your head?
No. But if you wanted to put in a line like this, that would be a regression. So that's something altogether different. Yeah.
It's still in there, but it's like
Yeah, I'll put together a video. The other issue is that when you're doing calculations, let's say that you have a column of C sub D values. Now, you've measured the time to probably, the accuracy of your time measurement is the 1/10 of a second, or maybe 100th of a second at most. And so if you're measuring your time to a 1/10 or a 100th of a second, and then you're measuring your volume, you know, if you think about what's the resolution of those little lines that are 1 liter apart, and how well can you tell 0.9 liters from 1 liter? Probably. But you probably can't differentiate 0.99 liters from 0.98 liters. And so there's a certain limit on the precision that you have in the data that you've recorded. And so when the C sub D value may be based on a flow rate measurement, to put in a table of values in your report that says, you know, you had a C sub D value of 0.7373427. If you list all of those values, what you're claiming is that you measured things so precisely that it was this and not that. You know, that's the level of resolution and confidence you have in your data. And so what I recommend is when you're displaying calculated results, now it's okay in the spreadsheet itself to leave it overly precise, although it just ends up being visually cluttered if you have lots of excess values. You know, if you're doing Q in liters per second, if you have a table and it's 11.2, you know, and you have a whole line of those, it's just visually cluttered. It's much better just to have displayed only the amount of resolution that actually was measured in the lab. And so 4 digits at most, and probably when you paste it into a table, 3 digits of accuracy would be more reasonable claim on the precision of your experimental data. And so excessive significant figures is just when you put a value down in a table, you're claiming that that's the value. And if you have lots of extra digits, you're basically saying that you had a super high level of precision.
Can you put them in scientific notation, especially if you have 0.
Sure. Yeah, if you have a lot of leading zeros, then scientific notation makes perfect sense, yeah. And the same thing is true on graph labels, just avoiding visual clutter. If it was 1.1, 1.0, 0.9, you know, for the K values, there's no need to put 1.1000, 1.1000, you know. Eliminate all of the excessive zeros where you can, and I'll include how to do that in the video tutorial that I put together as well. Subjective statements should be avoided, and remember, subjective statements are things like the lab went pretty well, the results are reasonable, and the reason why those should be avoided is because if you've only run an experiment one time, you don't have sufficient experience or authority to know whether or not the data and results are reasonable, really. It's better just to avoid any sort of claim that requires judgment and just stick to the data itself and interpreting possible reasons for why the data is, but avoiding subjective statements, and of course avoid the first person. That means don't say I, we, my, our. Don't refer to yourself during a lab report. And the reason why I think it's customary to do that in technical writing is that we're trying to be dispassionate. The experiment is not about us. The experiment is about the phenomenon, and so it's to take the attention away from the personalized aspect of it and make the report simply about the experiment that was conducted and not the people who did it. And then lastly, of course, there's always going to be errors in measuring time because you used a stopwatch. And of course, maybe the ball was dropped a little bit late from when somebody said go. But those are relatively minor sources of error compared to things like when we were doing the Venturi lab. The main reason why the energy grade line wasn't flat, if we have the head graph, remember the head versus tap number, we had the EGL gradually declining like so, and the HGL dipped quite considerably before it recovered, something like that. And so we had the EGL. The reason why the EGL wasn't perfectly level has nothing to do really with the stopwatch error or with volume measurement errors. The main reason is because Bernoulli's equation doesn't apply when you've got an inviscid fluid. And so the students who mentioned as the main error source the fact that we aren't honoring the 4 assumptions implicit in Bernoulli's equation, remember that they are along a streamline for an incompressible inviscid fluid and conditions are steady over time. But one of those that we were violating the worst was the fact that you're supposed to use a fluid that has no viscosity, but water does have viscosity. So there were energy losses through that Venturi. And so there are certain error sources that it's okay to mention. They're always going to be there, the human error sources, but then the real heart of why there was a steady decline in EGL was because, not because of human error, but it was because of misapplication of Bernoulli's equation in a case that it really doesn't apply in a perfect way. It applied okay, just not in a perfect way. So in general, I'm very pleased with the labs, and I mean, you should already know that from the high lab grades that I've been handing out. This is probably the semester that I've given out higher lab grades than ever before. I think in general you're doing quite well, but those are a few things that I wanted to point out so that you can improve even further. All right. Any other questions? All right. Well, today we're going to be talking about the continuity equation. And just to start things off, I wanted to show you about a dam and reservoir in South Dakota. It's called the Oahe Dam. And you can tell that it's what was originally a river system that's been artificially dammed. Here's the dam. You can see that straight line there is clearly man-made. It is quite a large reservoir, and it's used to generate electricity. If we zoom in on the dam itself, there's a couple of ways that water exits the reservoir. First of all, there are release gates here that are used primarily when the flow coming into the reservoir is very high. These release gates are kind of like an emergency measure. The more typical thing is for water to be flowing through the power plant. And there's a tunnel between the intake and the power plant. And so the water is going through turbines that generates electricity. When water goes through these emergency overflow release gates, then electricity isn't being generated. It's just they use those to get water out of the reservoir when the rains are very high upstream. so that water doesn't go over the face of the reservoir. You wouldn't want water just going over the top here. There's no spillway. Sometimes dams have spillways that are intentional so that when the water gets to a certain level, it's okay for water to go over the face of the dam, but in this case, water exits through those two locations. Now, here's another view of the power plant. You can see that there's a series of electrical turbines that are generating power. It's a relatively low head. There's not a huge elevation difference between the water in the dam and the water in the lake. I mean, compared to the Hoover Dam, which has a huge vertical distance, this is relatively low head. But back in June of 2011, there were some really heavy rains. It was quite wet in North and South Dakota. The watershed that drains into the Oahe Dam was receiving a ton of water. And so they had to open up the spillway. They had full capacity going through the power plant, which is approximately 50,000 CFS going through the power plant. And then they had about 110,000 CFS going through the spillway gates. And so first of all, before we calculate the water velocity through those gates, I thought I'd show you a couple of videos related to the situation. Beautiful sight. All that water coming out. suction shoots this other one. I frankly don't remember what this one is. We'll be jumping in in this example that we're working here. And so you wouldn't think that all of that water, that's a ton of water, and it's because it rained a little bit in the watershed upstream. You know, you're not having, all that water's coming out here because in the watershed that flows into the reservoir, it was raining, the soil was saturated, and so the water flows over the land and through small creeks, fills the reservoir. The reservoir can only go so high before there's a risk of it flowing over the top of the dam. And so that's why they have to do one of these heavy-duty controlled releases. What we were looking at was in here. The guy was walking around probably along that railing. Okay, so let's work this example here. And what we're going to be using is the continuity relationship. Start off by finding how much flow is going through each of the release gates. And then well, let's do it together. Excuse me. So through the gates, the total flow is 110,000 CFS. That means that the flow rate through each gate is going to be 110,000 CFS divided by 6. Of course, CFS is cubic feet per second. So that means that each one of those chutes has 18,333 cubic feet per second. What's the cube root of this, by the way? Let's just think about what sort of if we had a block of water, how big would that block be? What's the equivalent size? 26.3 foot cube, or foot on 26.3, 26.3. That's big. I mean, that's certainly taller than this room. I mean, that may be more than the volume of this room. Every second, that much water is going through each one of those 6 gates. So we're talking incredible quantities here. Each one of the gates is 19-foot diameter. I looked that up. I found some information online about the overflow. And for a diameter of 19 feet, we can find the cross-sectional area. Pi 19 feet squared divided by 4. 283.5 square feet. Now the continuity relationship that we're going to be applying here is Q equals VA. We'll talk about the fundamentals of that a little bit later, but as it's applied here, if we want to know what's the velocity of water as it goes through the gates, it goes through the pipes that lead to that outlet, it's Q divided by A. So 18,333 cubic feet per second divided by the cross-sectional area. And so the velocity is 64.7 feet per second. We probably wouldn't have to hold our breath for very long. You know, that's moving along pretty fast. Of course, if you banged your head on the side of the pipe as you're going through the pipe, it'd be lights out. But at least you wouldn't have to hold your breath long. That's a really high velocity. And it just sort of illustrates the implications when you combine fluid mechanics, hydrology, and hydraulics. We'll get into cavitation a lot more next semester when we are in 331, because cavitation is something that you have to avoid not only in pipelines coming from reservoirs, but also just any time you use a pump, there's a risk of cavitation. And so if you think about all of that water is going through a pipe, if the pipe starts to scour and erode, then there's a lot of energy being expended there, and things could just fall apart explosively, kind of like they did in the picture of that Russian power plant. And the photo of that Russian power plant makes a lot more sense when you see the flow going from the Oahe Dam. You know, this Russian power plant has a much higher head differential. You know, look at how tall it is. And so when it failed, the water was going through these penstocks, as they're called. The tubes are called a penstock when it takes water from a reservoir to a stream. And that's how a nice, tidy power plant turned into a heap of scrap, is cavitation. Where I left off in following the story was just that they confirmed it was cavitation that caused the incident. I don't know whether they've rebuilt it. I would imagine they probably did, because once you put a dam in, you know, it's there for good. It's, I think, unheard of that they'd abandon a dam. So I ought to check up and see what's the story with that now.
The dam in South Dakota, how we saw it, was like splashing over the ditches and everything. It was so sporadic. What is that, just because it's a high velocity rather than like just coming out pretty uniformly?
That's a good question, because I was looking at videos yesterday, and to contrast that, high flow outlet, let's see, I looked at one, yeah, here it is, high flow experiment. This
Down
shows a bunch of
Stewards.
politicians. Curvature of the pipe, the material of the pipe, you know, how smooth it is. You know, the reason why the water was splashing all over the place was because of turbulence, and there's things that you can do with the pipe to try and guide the flow and have conditions be as minimally turbulent as possible, but it's tough to say precisely why it was splashing so much. All right, well, here are the fundamental basics behind flow rate. And volumetric flow rate as units of cubic meters per second when we're working in SI, cubic feet per second when we're in traditional units, and the V bar here means average velocity. And although sometimes I'll just write V because I may be being sloppy and quick about it, really what I ought to say is V bar, because V bar means the average velocity across the entire pipe's cross-section, whereas V means the velocity at a certain point, you know, being more specific about it. But here in this case, if you measure the flow rate going through the pipe in volumetric terms and then you divide it by the cross-sectional area, then you'll get the average velocity, and vice versa. Here you can see that the element of water is traveling a distance during the time increment delta t. Mass flow rate is the volumetric flow rate times the density. And the units are a little bit different here in mass flow rate. Instead of cubic meters per second, if you multiply by density, remember density is kilograms per cubic meter. So if you multiply that by the volumetric flow rate, which is cubic meters per second, it'll cancel out the cubic meters, and mass flow rate, which is denoted by m dot, is kg per second. Or if you're working in traditional units, then it would be slugs per second, because slugs is the British gravitational system unit of mass. When you are applying the continuity equation, there are a couple of things that can cause volumetric flow not to be conserved. When we were talking in the lab on Tuesday about the continuity equation, what I had you do is think about the pipe. And, excuse me, sometimes when we introduce the idea of pipe friction, you know, the water is flowing from 1 towards 2, so the flow rate is this way. Remember, there's this thing called pipe friction. Pipe friction is a little bit different from the friction that acts on your car. If you're driving down the road and you turn off the car, you'll continue to coast for a while, but because of the friction of the tires on the road, because of wind resistance, you're going to start slowing down. So the frictional resistance causes your velocity to decrease in a car. The effect of pipe friction as flow goes through it, it's not that the velocity decreases, because if you have a certain amount of water entering the pipe, let's say that we've got a liter in the pipe, and that liter is right here. Assuming laminar conditions, then it's still together as a nice tight unit. Even if conditions are turbulent, it's not going to be together as a tight unit, but a liter goes in and a liter has to come out. There has to be no storage inside of the pipe, and so since there's no accumulation that can happen in the pipe, what goes in has to come out. Now, if you're working with a gas, though, gases can compress, and so the mass flow rate may be constant, but the volumetric flow rate may not. So the volumetric flow rate, Q in equals Q out for a liquid for sure, and you can apply Q in equals Q out for a gas as long as you assume that the gas isn't compressing and that its volume isn't changing as a result of compression. But mass flow rate is a lot easier to say that mass is conserved, because regardless of whether the gas is compressing, the same number of molecules go in as go out in a certain period of time. Back to the definition of mass flow rate. Since we define Q as area times the average velocity across the cross-sectional area, then m dot is simply the volumetric flow rate Q times the density. Any questions so far? Yeah. Flow rate. Yeah. So if we look at the units of these things here, yeah, density is kilograms per cubic meter, flow rate is cubic meters per second, and so mass flow rate, m dot, has units of kilograms per second. The velocity isn't the same everywhere in the pipe. Because of pipe friction, the velocity is lower at the edges of the pipe than it is at the center of the pipe. And what this figure is showing is the velocity distribution. There's a curvature here. It looks like a bullet shape almost in this diagram. And you can find the average velocity by breaking the cross-sectional area up into lots of little elements. And if you know the velocity for each one of the elements, you can come up with a weighted average. So what causes that velocity distribution is is pipe friction, the resistance to flow that the liquid is moving through the pipe and it's in contact with the pipe that is stationary. And since the liquid has viscosity, there's a resistance to movement, and it causes the velocity distribution, where the velocity is the fastest at the center of the pipe. And so another way of finding the flow rate is, even if the velocity isn't the same everywhere in the pipe, in this earlier diagram, the velocity was the same everywhere. It was a flat velocity distribution. But you can account for the fact that the velocity isn't the same everywhere in the pipe if you integrate the elemental areas and multiply them by the velocity of each area element, and then take all of the pieces and integrate for the entire cross-sectional area. And so you can find that in terms of volumetric flow rate Q or the mass flow rate. And this is showing another look at the velocity profiles. And what we know is that in laminar flow, meaning that the conditions are such that the Reynolds number is less than 2,000. So if the Reynolds number is less than 2,000, typically what you'll have is a very smooth velocity profile. And the velocity at the center of the pipe is double the average velocity. The average velocity is, if you draw a line through the velocity profile, half of what's under the curve would be to the right of that line, half would be to the left of that line. But in turbulent flow, the average velocity and the velocity at any particular point are very close together. So let's apply the concept of mean velocity, and why don't you calculate the mean velocity and the volumetric flow rate, where what you're given here is a mass flow rate. So we know the density of the oil, the mass flow rate, that's m dot, and I'd like you to calculate the velocity of the oil through the pipe and what's the volumetric flow rate. Alright, so if the mass flow rate, m dot, is 550 kilograms per second, and we know that the cross-sectional area of the pipe is pi 0.5 meters squared divided by 4. So the cross-sectional area is 0.19635 square meters. Mass flow rate is defined as the density, the area, and the velocity. So the velocity is the mass flow rate divided by the density times the area. So 550 kilograms per second. The density here is 850 kilograms per second. I'm sorry, kilograms per cubic meter. And then the cross-sectional area we've just calculated at 0.19635 square meters. So the units are going to cancel out. The kilograms go away. The seconds stay. And combining the units here, the meters cubed in the denominator of this expression, the meters squared there, it's going to give us the velocity is 3.295 meters per second. And then the volumetric flow rate, we could calculate that one of two ways. We can either just multiply the mass flow rate by the density, or since we've already got the velocity, we could get Q equals VA. And so 3.295 meters per second times the area of 0.19635 square meters, 0.647 cubic meters per second. There we go. All right. Any questions on the example? Probably you put in the specific gravity instead of the density of the oil, I would guess. All right. there's something in Chapter 5 that's referred to as the control volume approach. And the control volume approach is meant to be a way of keeping track of mass and how it flows in and out of a system. And the abbreviation CV is used throughout several problems and in figures to stand for control volume, and CS stands for control surface. In the control volume approach, a system is defined as a continuously connected mass of particles. It's the same kind of fluid, and it's connected by being in contact with the fluid. The mass of the system is constant. The location of the system can change, but the number of particles that we define as the system remains steady. The control volume is the area that's enclosed by the control surface, and it's just an imaginary shape. It doesn't actually exist necessarily, although sometimes we'll say we're going to put a control volume around a tank and then keep track of what's inside the tank and what goes in and out. The idea here is to establish a boundary, and you're performing accounting using that boundary. You want to find out how things move into the boundary, out from the boundary, and then look at what's inside of it and how the mass of the system inside of the control volume changes over time. The control surfaces surround the control volume. And so here, what's depicted is a pipe with a changing diameter, and you can see a curved surface here, that the control volume is some imaginary boundary that we draw between 2 points, and the purpose of that is to predict what the velocities are going to be. And so there's a velocity coming in, a velocity going out, and since the control volume is already completely full of the system, meaning that there's only water in here, there's no capacity for additional storage inside of this control volume, any mass of the system that comes out into the system at 1, into the control volume at 1, is going to cause a certain number of particles to be ejected out of the system at 2. You can also apply the control volume approach to a location that does have the potential for storage. You know, here in a pipe that's already full, there can't be any storage, but in a tank there can be storage. And there's a figure in the text that illustrates the control volume approach kind of graphically. And what it does is says control volume is inside of the tank, and consider conditions at time t. So at time t, these dark blue elements here are what we're going to call the system, and what's in light blue is not included in the system. So at time t, some of the system is in the tank and some of it is into the pipe that's flowing into the tank. At time t plus delta t, so that's a little while later, all of the fluid that was inside the inlet pipe is now either in the tank or some of it is discharged. What you'll notice is that the liquid level's a little bit lower here. Look at how the water, or whatever this liquid is a little bit higher in the tank at time t than it is at time t plus delta t. The liquid level is lower. And the reason for that is that there's more in the outflow pipe here at this time. The length of that dark blue segment is deeper and longer than the amount of water that was in the inflow segment at time t. So the options that the water faces as the water enters the tank is it can either exit the tank or it can be stored. And so there's probably some sort of a control valve at the exit of the tank that can be opened or closed, and the operator can control the volume of liquid that's stored in the tank by changing how much is allowed to flow out of the tank over time. Again, the system, the number of particles in the system over time is constant, but it's the location that we're going to keep track of in this control volume approach. The control volume approach says that the mass of particles in the system at time t, it's the mass that's in the control volume and the mass that is in the inflow tank. Now this isn't a general law. This is just saying at this particular time the system is in 2 places. There's the liquid that's in the tank and the liquid that's in the inflow. At this time a little bit later, the liquid that is part of the system is in the tank and there's a certain amount in the outflow tank. In general though, this is a general law now, the change of mass in the control volume is in minus out. And it's on a mass basis that we keep track of these things because mass is conserved. It can neither be created nor destroyed. what I'll sometimes abbreviate this expression as, sometimes just out of habit, I'll say accumulation is in minus out. Accumulation is in minus out. So what that means is that if you have some sort of a control volume and there's more flowing into the control volume than is flowing out, the accumulation will be positive. That would be a tank with the water level rising. But if out is bigger than in, then the liquid level will be declining because the accumulation is negative in that instance. It's simply just accounting. It's looking at where is the mass and how is it changing over time. We can say that the change of mass inside of the control volume over time is equal to the rate. Now, the difference between m and m dot is in m, we were just talking about a static amount of mass. But with m dot, that's talking about a mass flow rate. And so there's an element of how things are changing over time. And thus, the change of mass in the control volume with respect to time is the mass flow rate in minus the mass flow rate out. Both of the lectures next week take this, this control volume approach and the continuity equation and apply it to several examples that illustrate how you can use the accounting of mass flow rate in and mass flow rate out to solve a lot of different types of fluid mechanic problems. There are some definitions that the textbook introduces that have to do with continuity equation, and that is that sometimes things can have extensive properties, and extensive properties are those that are proportional to system mass. So how much mass there is in the system is going to reflect how much mass there is, how much momentum there is, and how much energy. If it's not related to how much mass is in a system, like the color of a liquid is independent of how much there is, or the viscosity of water doesn't vary based on the amount of it, some properties don't vary as a function of how much mass there is, and those are called intensive properties. I think there's a question in your homework assignment that asks you to compare extensive and intensive properties, and there's a lot more in the textbook that describes the difference between the two. The thing to keep in mind, though, is as we're accounting for fluids and how they move from place to place, their properties are transported along with them. So back to the example that's shown here, if this liquid was kerosene, for example, what's being transported is energy, because energy is a function of the mass of the system. How much mass there is reflects how much energy there is. And so instead of just keeping track of how the mass is changing over time, we could look at how the amount of energy inside the control volume is changing over time. How many joules are present there, if it's a flammable liquid maybe. Or if we're talking about momentum, you can keep track of the accumulation of momentum inside of a control volume. Chapter 6 is where we start to get into detail about the momentum of systems. The Reynolds transport theorem is just the fancy way of expressing this idea: accumulation is in minus out. This is the simplification of the Reynolds transport theorem. And so the Reynolds transport theorem is presented on the screen here, and it has two parts. It's got a storage part and a transport part. And if you look at these two terms, there's the control volume, CV, and in the storage term, what we're concerned with is the change in volume over time. So D and then the V with a cross through it, that V means volume. This other V here, without the cross through it, that means velocity. So in the storage term, if you know the mass of the, if you know the density of the fluid, and you know the rate that the volume is changing over time, then that tells you how much storage changes over time. And transport is talking about the difference between the in and the out through the control surfaces. And so you multiply the density by the velocity and the cross-sectional area, like we did in this example just a few moments ago. That's the mass flow rate. And the net mass flow rate in versus out is what accounts for change in storage. So in other words, in the Reynolds transport theorem, if you say we're going to simplify the Reynolds transport theorem so that dm dt is equal to 0, the mass of the system is constant, mass is not being created or destroyed, it's just an ordinary situation, like there's no radioactive decay, it's just the conservation of mass applies, So if you set dm dt equal to 0, then what results is the change of mass in the control volume. This is the storage term, or accumulation is the mass flow rate in minus the mass flow rate out. Well, I've kept you 1 minute over. I apologize for that. It's easy to get carried away when you're talking about the Reynolds transport theorem, though. So remember that next week our lectures are online. Those are available now. I'll email you the links, and I'll also make the links available through MU Online. Feel free to take another caramel for the road if you'd like, and I'll see you on the 5th of November.